Hi everybody. In this video, I would just want to do a quick review of vectors to kind of refresh your memory for some Physics 5a stuff. I also plan to record a couple other videos going over Newton's laws and also conservation of energy to also review Physics 5a stuff. But for today, we're going to talk about vectors, just a quick overview, nothing too in-depth. Let's go ahead and get started. So first of all, what do we mean when we talk about a vector? Well, a vector is a quantity that has magnitude and direction. And we can represent a vector quantity graphically with an arrow. Like so. So here's a vector, just call it A. Right, this is in contrast with a scalar. A scalar is just a number. So a scalar doesn't have a direction associated with it. All right, now we can represent a vector graphically by an arrow like this. How do we actually write down, as like a formula, a vector? There's two different ways we can represent a vector. One is, since we know a vector is a quantity with a magnitude and a direction, well, we can just give the magnitude and the direction. I should mention, when I say that we're representing a vector by an arrow like this, the magnitude is represented by the length of the arrow, right? The magnitude of the vector is like the amount of whatever quantity we're looking at, and then the direction of the vector is just the direction of the arrow. Okay. All right, so we give the magnitude, we give the direction. How do we specify the direction? There's various different ways we could do this. If we have a coordinate system, we could say, and our vector happens to lie along one of the coordinate axes, we could say the vector is along the x direction, along the y direction, or we could say the vector points left or right or up or down. But, if the vector points in some arbitrary direction, to specify that direction, typically what we do is we give the angle of the vector from one of the coordinate axes. Okay, and conventionally, the axis that we choose is the positive x-axis. Okay, so when we talk about the angle of a vector, okay, let's say this is a different vector b, right? We're talking about not what I wanted to do. This angle here, right, measured from the positive x-axis. We could give a different angle if we wanted to, right? I could specify this vector by giving, this angle from the positive y-axis or giving this angle from the negative x-axis or something. But the convention is to use the angle from the horizontal, from the positive x-axis. Okay, so that's one way to represent a vector. Another way is to give the components of the vector. And the components are the projections of the vector onto the coordinate axes. Right. So, for example, for my vector, do two different examples here. So, say vector A, B. Right? What do I mean by the projections? Well, if I drop a line down from the tip of the vector, or not down, but if I drop a line from the tip of the vector to each axis, wherever that line lands on the axis, that's the component, right? So for example, here's the x-axis, y-axis. This value here would be the x component of A, and this value here would be the y component of A, right? And same thing for B. Okay, this would be B sub y, B sub x. All right, and these components can be positive or negative, and the sign of the components tells us information about the direction of the vector, right? For A, both of these components would be positive, and for B, the y component would be positive, the x component would be negative, right? That's telling us the vector points along the negative x-axis, but it points along the positive y-axis. So if I wanted to write out these vectors in terms of their components, one way to do this is to write it like this. Okay. All right, so a couple things we want to be able to do with vectors. One thing we want to be able to do is decompose vectors. And that means we're given the magnitude and the angle, or the magnitude and the direction of the vector, and we want to find the components. Okay. So we can do that using trigonometry. Right. Suppose, this is my vector A. And let's say I have this angle from the positive x-axis. All right, so here's my x component and my y component. And this gives me a right triangle where the hypotenuse of the triangle is the magnitude of the vector, the length of the vector, and then the sides of the triangle are the components. Okay. And so if I want to find the components in terms of this hypotenuse here, right, I can just use, I can say sine of theta, that's opposite over hypotenuse, which means a sub y is a sine theta, and cosine theta is adjacent over hypotenuse. That's a sub x over a. Go ahead and mute for the helicopter for a moment. So I end up getting, in terms of this angle theta here, specifically this angle, these are the components, right? All right, now this only works in the case where theta is this particular angle. Right, so it has to be the angle I've drawn here from the positive x-axis. If it's any other angle, then I'm going to need to draw a different triangle, and the trigonometry is going to work out differently. Right, so for example, let's look at B. And suppose I had this angle here, call it phi, from the positive y-axis. Okay, now my triangle is going to look like this. So the magnitude is still the hypotenuse, but now my opposite side here is minus a sub x, minus because the x component of b is negative, and the adjacent side is a sub y, right? So I get different formulas. Oops, sorry. These should be b, not a. Okay, right? I get different formulas in terms of that angle for what the components are. So just take care when you're decomposing a vector. If you're given the angle from the positive x-axis like this, then you can go ahead and use, these formulas. Maybe I'll put the color in here so make it clear it's for the specific angle, right? But if you have another angle, then you'll have to actually draw the triangle and do the trigonometry to work out what the components are. All right, another thing we might want to do is get the magnitude of the vector from the components and also get the direction of the vector from the components. And again, we can use trigonometry for this. Right, so let's just look at our vector A, for example. So again, the magnitude is the length of the vector, which we're thinking of as the hypotenuse of this triangle. Right, and the sides are a sub x and a sub y. So the magnitude is related to the sides by the Pythagorean theorem. Okay, so I have this formula for the magnitude of the vector in terms of the components. And if I want to get the angle, and again, this is specific to the case where I'm talking about the angle from the positive x-axis, then I can also use trigonometry. I can see that tangent of theta is equal to, so that's opposite over adjacent, that's a sub y over a sub x. And so theta is inverse tangent of a sub y over a sub x. Okay. All right. Another thing I want to be able to do with vectors is add them. Now I can do this graphically. If I have two vectors, let's say A and C. Okay. If I want to add these two vectors to get a new vector, then the graphical way to do it is using something called the tip-to-tail method, or the parallelogram rule. Right, and what this says is I take the tail of C and place it at the tip of A, okay, and then I draw the vector from the tail of A to the tip of C, and that gives me the sum A plus C. Okay. And this is called the parallelogram rule because I can also do this by drawing a parallelogram where the sides of the parallelogram are the vectors, and then the sum of the two vectors is the diagonal of this parallelogram. So in practice, we don't use this that much, although it's useful if you want to see, for example, if you're adding two electric fields and you want to graphically determine what the final field is, this can be useful. In practice, what we do when we add vectors is we do it in terms of the components. So the way vectors add working with the components is pretty simple. What we say is that the two vectors add component-wise. And all that means is if I want to add a plus c, or whatever two vectors, then to get the x component of that final vector, I add the x components, and to get the y component of the final vector, I add the y components. And the same thing works for subtraction. If I wanted to subtract two vectors, I would subtract the components. Okay, the last thing that I want to be able to do with vectors is to multiply them by scalars, multiply by a number. Okay. So when I do this, when I multiply a vector by a scalar, the reason we call them scalars is because multiplying a vector by a number scales the vector. And what I mean by scaling the vector is I increase or decrease its size. Okay, so for example, if this is a, 2 times a is a vector in the same direction, which is twice as long. Okay. And if I were to multiply a by 1/2, I would get a vector pointing in the same direction that's half as long. Now, if I multiply it by a negative scalar, then I get a vector that points opposite the vector I started with. So if I were to draw negative 2 times a, I get a vector in the opposite direction that's twice as long. In terms of the components, when I multiply by a scalar, that just scales both of the components. So if I have a scalar c and I multiply by a, then the components just get multiplied by c. The last thing I'll mention is just bear in mind that when we add vectors, you have to be careful because you might want to say that, if I add two vectors, that their components, when I add two vectors, that their magnitudes add up. And I want to warn you that that's not the case. Okay, and I just want to give you a simple example of that. Let me draw two vectors, call them D and E. Okay, and these could be, have any x component here, but let's just say D is the vector 2, 0, and E is the vector in the opposite direction, -2, 0. Okay. And when I add these up, okay, clearly I'm going to get 0 because I'm just taking 2 minus 2 and 0 plus 0. So I get 0, 0. So the sum of these two vectors has a magnitude of 0. Right, but each of these vectors individually, their magnitude is 2. So if I were to add the magnitudes of these two vectors, I would get something non-zero. I get 4, which is not the same thing as what I get when I add them first and then take the magnitude. And this thing here on the left is not really something that you ever want to do. It's very rarely, if ever, useful in a physical context to add the magnitudes of vectors like this. So typically what you want to do, in fact, all the time really, is add them first and then take the magnitude, right? So if I were to add these two vectors, or any two vectors, right, what I'd need to do is, and I wanted to get the magnitude of their sum, I would need to add up the components, right, and then I can take the Pythagorean theorem to get the magnitude of the vector sum. Right? But don't make the mistake. I've mentioned this a couple times because this is a really common mistake, and I want you to be aware of this so you don't make this mistake, right? Don't make the mistake of adding the magnitudes of the vectors. Okay, that's everything I want to say about this. There's plenty more we could say about vectors, but that should be all we need as far as this class. So thank you, everybody. Take care, and I'll see you later. And make sure to check out my other 5A review videos. I may not have them posted yet, but I should have them posted soon. See ya.